Hello and welcome to your first example that is going to go straight into your acid-base notebook. This is going to be a video about how you can use Kw with pH to calculate concentrations as well as pH and pOH. Alright, so there's our question. So we're going to do this in steps. Step 1 is going to be to identify the major species. Identify major species. So in this case, the acid or base that is reacting is water. And it's good to note whether this is a strong or weak acid or base. And in this case, water, you should know, is weak. Now, we're going to write down our reaction. Now these first two steps are basically the same for any problem you're going to do in this chapter. So you'll identify your major species and you'll write out your reaction. So H2O, which is a liquid, is going to react double arrow. Think to yourself why this might be a double arrow. So hopefully you thought it should be a double arrow because it is weak. If you have a weak acid or weak base reacting, it can reach equilibrium. They do not completely dissociate. It kind of bounces back and forth. So make sure you use a double arrow on those. So next, you're going to write out the equilibrium expression. So this is from our last chapter. We're going to write out our K, I'm going to put purple for that. We're going to write our Kw. And I'm saying Kw because this is water. If it was any other reaction, if it was like a weak acid or a weak base, you'd have Ka or Kb. But water is special, so it gets Kw. And since we know H2O is a liquid, do we include that in our Kw? Hopefully you said no, we don't. It's a liquid. We don't include liquids or solids, just aqueous solutions and gases. So here are my products. They go in the numerator. I have no reactants, so it's over 1. And we know, because we have this memorized, that Kw is equal to 1.0 times 10 to the negative 14. Oops, that should be a 4. Something to note, though, is this number here and any other Ka or Kb that you could need in basically any situation is going to come from a chart. So this comes from a given chart. And for your notebook, you're going to be printing out a list of Kas and Kbs to be able to reference when you do these problems. Okay, so before we move on, I want to ask, if our problem involved a strong acid or a strong base, would we be writing an equilibrium expression? Your answer should hopefully be no, because if we have a strong acid or a strong base, we would draw a one-way arrow. It would not reach equilibrium. There is no equilibrium for strong acids and bases at all. None. It doesn't happen. We would follow a different path for those, which we'll do in a later video. Okay, so now we're going to set up an ice chart. Which you've had lots of practice on now, so you should be like, oh goody, I know how to do these. Our goal is to figure out the concentration of hydrogen and hydroxide. We're not given a lot of information except for our Kw and our starting concentrations, so let's just see what we've got. ICE. E, initial change equilibrium. I have H2O H plus OH minus. Okay, so let's think about what we're starting with here. Water. We started with water. However, water is a liquid, so I'm just going to go ahead and do this. It doesn't go on the ice chart. But we started with water, which meant we did not have any hydrogen or hydroxides. So good, we have our initial concentrations, but it doesn't tell us anything else. So if it doesn't tell us anything else, we have nothing in the equilibrium line. What do we have to do? We have to assume something is X. So we're going to be gaining an X amount of hydrogens, and since they have the same coefficient up here, we'll also gain an X amount of hydroxides. 0 plus X just gives you X. 0 plus X again gives you X. And we have finished our ice chart for now. So let's move on to step 5. We're going to plug everything that we have into the equilibrium expression. Plug into equilibrium expression. So we wrote the equilibrium expression over here in step 3, so I'm just going to copy it down first. I know Kw equals my hydrogens and my hydroxides. And I know it's equal to 1.0 times 10 to the negative 14th, but first I'm going to plug in my x's. So here I have x times x from the ice chart is equal to x squared, and we know that Kw is equal to 1.0 times 10 to the negative 14th. Come on, 4, you can do it. There. Okay, so knowing that, if I take the square root of both sides, I will get x is equal to 1 times 10 to the negative 7. I'm carrying my sig figs through. 1.0. And I know that x is the same thing as my equilibrium concentration of hydrogens, which is right here, and my equilibrium concentration of hydroxides. So I can just take this number and say that, and this is an answer, so I'll put it in a different color. How about, I don't know, I guess we'll just do red. So the concentration of hydrogen is equal to 1.0 times 10 to the negative 7. If the concentration of hydrogen was equal to 2x, then I'd multiply this number times 2. And this is a concentration. What are the units of concentration? They are molarity. Now my hydroxide is the same in this case, so 1.0 times 10 to the negative 7 molarity. So that's part of my answer. It was asking for those equilibrium concentrations. But we're not done yet. We also want to know pH and pOH. So step 6 is to calculate pH and pOH. So from the last video you learned that pH is equal to the negative log of the concentration of hydrogen ions. If you didn't know that, now you do. So pH is equal to the negative log of the hydrogen ions. So if I were to plug in 1.0 times 10 to the negative 7 into here, negative log of 1.0 times 10 to the negative 7. If I plug that in my calculator, I will get a pH of 7. So that's an answer. Let me put that back into my fun reddish-orange color. pH equals 7. So here's something interesting you need to know about logarithms. When you put something through a log, we had 2 sig figs, right? This was 2 sig figs. whatever comes out, the sig figs only count after the decimal. This, since it's coming through a log, 7.00, those are 2 sig figs right there, because we know that this is actually from a log. That is 2 sig figs. Kind of weird, I know. You'll just have to get used to it. So now we also learned recently that pH plus POH from a reaction is always equal to 14. So what we could just do is say, all right, POH is equal to 14 minus pH, which we just calculated, and that's right, we are basically done. Our POH is equal to 7. And again, we want 2 sig figs, and these are coming through logs, so it would be 7.00. So I'm just going to write down that note about the logs, so that way you don't miss that. So I'll put that down here. Note. Log sig figs come after the decimal place. So, for example, that is 2 sig figs. Alright, so there you go. Here is your very first problem from this chapter. If you start with a weak species, then you're going to write out your reaction and create an equilibrium expression, because weak acids and bases go to equilibrium. You will use an ice chart to figure out concentrations, and then you can plug those concentrations into these formulas that involve logs to figure out their pHs, and then you're done. So I hope this video was helpful, and I will see you later.